Hello friends, a warm welcome to our next session on instrumentation and control in power plant industries. In our first session on temperature measurement, we have discussed about the various types of temperature measuring devices used in a power plant. Then our next session was focused on thermocouples in details. In this session, we will discuss about RTDs, that is resistance temperature detector, in detail. Today we will cover the topics: what is an RTD, its principle of working, why does resistance change in metals with temperature, measurement circuits used for getting useful information out of this resistance change, what are the different parts of an RTD, basically the construction component of an RTD. Then we will briefly touch about RTD installation and what are the different types of RTDs based on their material of construction. Then we will cover about 2-wire, 3-wire and 4-wire RTD configuration. What are the various advantages of using RTDs? And last but not the least, we will cover few disadvantages or limitations of RTDs over other instruments, particularly as compared to thermocouple. So friends, an RTD or resistance temperature detector is a type of temperature sensor that operates on the principle that the electrical resistance of a metal increases predictably with temperature. Simple, resistance is getting increased with increase in temperature in a predictable manner, that is linear manner. RTDs are commonly used for temperature measurement and control in various industrial and scientific applications. An RTD is basically a passive temperature sensing device, and RTDs have positive temperature coefficient, means their resistance increases with increase in temperature and resistance decreases with decrease in temperature. However, this resistance cannot be directly used to calibrate into temperature reading. So to measure the temperature using an RTD, the device is connected to a measurement circuit. The measurement circuit converts this resistance value into corresponding voltage output using either Wheatstone bridge or by using constant current source. Different metals behave differently when exposed to temperature. An RTD could be made up of platinum, copper or nickel. Our platinum RTD Pt100 is the most commonly used RTD in power plant industry. Then friends, we may have the question, why does this resistance change in metals with temperature? So we know materials are made up of atoms. All materials are basically made up of atoms, and these atoms each and always vibrate due to their potential energy stored in them. And when we connect these conductors to a closed electrical circuit, the current starts to flow through it. We know current is basically a flow of electron. So these flowing electrons in the conductor collide with the vibrating atoms. Sorry. Till now it's clear. All materials have atoms that constantly vibrate due to their stored energy. And when we connect it to an electrical circuit, then current starts to flow through them. And current is basically a flow of electron. On one side, atoms are vibrating, and on other side, electrons are passing. So these atoms basically uh, create a restriction basically. So these flowing electrons in the conductor collide with the vibrating atoms, thereby decreasing their speed. This property of opposing electron flow, that is opposing the flow of current passing through it, is called resistance of that material. Now coming to the question, why this resistance is getting changed. So on heating this material, the atoms absorb the heat energy and thus vibrate at much faster rate. So we can say this the collision of the atoms with the flowing electrons is also increased, and thus the resistance value is increased. Clear? On heating, atoms absorb the heat energy and then starts to vibrate. much faster. So if atoms are vibrating at much faster rate and electrons are trying to pass through them, then definitely the collision rate will be increased, thereby restricting the flow of electrons. Means now lesser current would be allowed to pass. That means this, we already discussed, this property is is nothing but the resistance itself. So resistance is getting increased with rise in temperature. Clear? Now, interestingly, we have two types of measurement circuits available to measure basically temperature out of this change in resistance. One is Wheatstone bridge and second is constant current source circuit. So first we will discuss about Wheatstone bridge. Basically, Wheatstone bridge was probably the most commonly used method originally, but it's not so common anymore. We will discuss other method, but first let's look at the Wheatstone bridge. Let's assume all the resistors in the Wheatstone bridge are exactly 100 ohms. These resistors R1, R2, R3 and the resistor Pt100 itself are exactly at 100 ohms. Then at 0 degree centigrade, the voltage V in the circle we have shown the voltage. Here we will measure this voltage. The at 0 degree centigrade, the voltage V will be exactly 0 volt. Now, if the temperature changes, the Pt100 resistance changes. We discussed in previous slide, and the voltage V also changes. So the value of the voltage change represents the change in the temperature at the RTD. Clear? As you can imagine, the distance between the RTD and the bridge becomes an issue because of the introduction of the lead wires resistance. This Pt100 is installed on the process line, and this measurement circuit, if it is not a local means direct temperature transmitter, then it would be transferred to the control system. So these lead wires would be longer than these lead wires itself having some resistance. So this lead wire resistance will produce error in the temperature measurement. Moreover, with the passage of time, this supply voltage is also getting drifted. So a drifting supply voltage is also problematic as it will affect the output measured, that is output voltage measured. As a solution means this new technique, the constant current source is getting used nowadays. So let's look at better RTD resistance detection method. This constant current source method is very popular. We know simply voltage is equal to current into resistance. Means the voltage V is direct result of the resistance of the Pt100 and the constant current flowing through it. Simply, and an increase in the lead wire resistance does not affect the voltage V because the current through the RTD is not getting affected. Clear? V is equal to IR. I is constant current we are telling, and this lead wires are still in series, so nothing means current will remain the same. So there is no effect of the lead wire resistance. Now coming to the construction, the most common part of an RTD device is its sensing element. In this picture, we can see at the tip of this instrument, this sensing element is located. This is the actual component that senses the temperature. Again, RTD device is an immersion type of device. Means they are immersed into the process fluid whose temperature we are measuring. So during RTD installation, it is ensured that this tip, which is having an RTD sensing element, is always immersed in the process fluid to measure its temperature accurately. In next slide, we will cover the types of RTDs based on the material of construction of this sensing element, which could be either platinum or nickel or copper or even Balco. Balco is basically nickel iron alloy. So as this sensing element comes in direct contact with the process fluid, the heat is transferred from fluid to this sensing element. As we discussed in its operating principle, its electrical resistance increases as its temperature increases and vice versa. For example, our platinum RTD Pt100 at a temperature of 0 degree centigrade shows a resistance of 100 ohms. But when the process temperature increases from 100 degree centigrade to uh, from 100 this whenever process temperature increases to 100 degree centigrade, the Pt100 sensing element's resistance changes to 138.5 ohms, and this change in resistance corresponding to the change in temperature is linear. Clear? Then next component of RTD device is our lead wires that connects RTD sensing element to the measuring circuit, that is the temperature transmitter, or as I mentioned, could be directly connected to DCS input output modules which are specifically designed for RTD measurement. First component, the main component is its sensing element, which is our platinum, nickel, copper. Then these sensing elements are connected to lead wires, and lead wires are getting connected to our either temperature transmitter or directly to our control system. Then to protect it, these lead wires pass through metallic sensor sheath that covers and protects most of the components of the RTD instrument. Basically, it's covering, and the empty space between the RTD sensing element and this sensor sheath is filled with the packing material, generally magnesium oxide. This magnesium oxide packing, what is the basic advantages? It reduces the vibration, surrounding vibration impact on this sensing element. Thus, it helps in more accurate measurement. Then we can see this process connection. For installation purpose, we need some kind of connection. Generally, we have a threaded adapter. So this adapter is welded to this sensor sheath so that we can have threaded connection on both sides of this adapter. Then our RTD basically now instrument is ready for installation in the pipeline. On one side of this adapter is threaded to the thermowell, or maybe direct connection to the process pipeline, or other side of this adapter we use to install our temperature transmitter, or simply a cold end termination for connection to DCS. I hope this construction of basically components of RTD is clear. Sensing element, then lead wires, then to protect it, this metallic sensor sheath, and inside this sensor sheath we fill it with packing material magnesium oxide. Benefit, it reduces the vibration impact. Then for process connection we have threaded adapter, both side thread connection, and then this one side of this thread connection we fit it to our thermowell or the pipeline. On other side we can install our temperature transmitter or this cold and termination for wire connection. Clear? Simple design. Next, coming to basic of RTD installation, the installation is generally not direct to our this process line, but using a thermowell. Thermowell basically protects our RTD. So what we generally do is the process pipeline is drilled. In this second picture, we can see this threadolet. So what we do is we generally drill the pipeline, typically 3 by 4 inch hole we create, and then a threadolet is welded over this hole. Then a thermowell, in on the right side picture we have shown many thermowells. Then a thermowell is inserted, and again it is having threaded connection, so that fits into this threadolet using thread connection. Then finally we insert our RTD in that thermowell, again with threaded connection. On top of this RTD we have this golden connection termination, or maybe in more advanced plants we use head mounted temperature transmitters, and from there we have final connections to our DCS system, the control system. Clear? Now coming to the types of RTDs. Basically, RTDs come in various types, distinguished by the material used, the temperature coefficient of resistance, and the nominal resistance at 0 degree centigrade. The most common types include the platinum RTDs. So our first type of RTD based on material construction is platinum RTD, and again in platinum we have three versions: PT100, PT500, and PT1000. This PT100 is the most widely used type, where the resistance is 100 ohms at 0 degree centigrade. It is made up of platinum and is highly accurate and stable. Now coming to PT500, it is also similar to our PT100, but its resistance, that is nominal resistance of 500 at 0 degree centigrade. Clear? Then we have PT1000. Again, PT1000 is also similar to PT100, but with a nominal resistance of 1000 ohms at 0 degree Celsius. PT1000 resistance are often used in applications where a high resistance allow for longer cable run without significant signal loss. Means if we have to transmit it to a longer distance, direct voltage signal, then we use PT1000. Otherwise, in a power plant, PT100 is used. Now coming to second type of RTD based on the material of construction are nickel RTDs. Nickel RTDs are less common than platinum, but they are still used in certain applications. And nickel shows a resistance of 120 ohms. We can see in this table, nickel RTD shows a resistance of 120 ohms at 0 degree centigrade. So we call it as Ni 120. Clear? So Ni120, nickel 120 RTD with a nominal resistance of 120 ohms at 0 degree centigrade is used. Our third type of RTD based on material of construction is copper RTD, Cu10, because they show a resistance of 10 ohms at 0 degree centigrade. These are less common than platinum or nickel and are typically used in specialized applications. Another type of RTD is Balco RTD. Balco is not a metal, but it's an alloy. It's a nickel and iron alloy to achieve a balanced temperature coefficient, reducing errors caused by the changing resistance due to strain or vibration. Now coming to the shape of RTD. So our next type is not based on the material, but the shape. This thin film RTDs are constructed using thin layer of resistive material such as platinum deposited on a ceramic substrate. They offer faster response time and are suitable for applications where space is limited. Again, based on the shape, our next type of RTD is wire wound RTD. Use a length of wire wound around a ceramic or glass core. While less common than the thin film RTD, they can be more robust and suitable for certain industrial environments. So what we understood is each type of RTD has its advantages and is chosen based on the factors such as temperature range, accuracy requirement, and the specific conditions of the application. Platinum RTDs, especially PT100, are the most prevalent due to their high accuracy, stability, and third is widespread application, standardization, sorry. Now coming to 2-wire, 3-wire, and 4-wire RTD configuration. Friends, we know the distance between the RTD and the measuring circuit becomes an issue because of the introduction of the lead wire resistance. An increase in the resistance will produce an incorrect temperature inference. Lead wires or connecting wires resistance plays an important role in the accuracy of the RTD instrument. The term 2-wire, 3-wire, or 4-wire refers to the configuration of the wiring used in connecting these RTDs to a measurement or control circuit. Each configuration has its own advantages and is chosen based on the factors such as accuracy requirement and then need to compensate for lead wire resistance. So coming to our first type, it is 2-wire RTD configuration, the simplest one. In a 2-wire configuration, an RTD is connected to the measurement circuit using the two wires, two sides of the RTD. connecting to two leads and two lead wires, and then directly connected to our measurement circuit. So simplest, basically advantages: simplest to implement, requires very few wires, which can reduce our cost. So two wire RTDs are cost effective, but definitely at the sake of accuracy. So if we talk about the disadvantages of two wire RTD configuration, the resistance of the connecting wires, these lead wires, introducing errors in the temperature measurement, as we cannot distinguish between the lead wire resistance and the Pt100, basically RTD resistance. Also, this two wire RTD configuration is generally less accurate compared to three wire and four wire configuration. Two wire RTD configuration is used in application where we require lesser accuracy, and the cost is a significant consideration because these are comparatively cheaper. Now our next type is three wire RTD configuration, where the RTD is connected to the measurement circuit using three wires. This third wire, additional wire, produces a mean of compensating for the resistance of lead wire, thus improving the accuracy. Thus three wire configuration is more accurate than two wire configuration due to this lead resistance compensation. However, this additional third wire not only brings more complexity than this our two wire configuration, but also increases the cost, and it is used basically in applications which require moderate accuracy while balancing complexity and cost. Additional wire definitely costs money, so cost increases, but accuracy is much better than two wire RTD because this lead wire resistance is compensated. Then we have most accurate, which is four wire RTD. In a four wire configuration, the RTD is connected to a measurement instrument using four wires. The advantage of four wire configuration is they offer highest accuracy and precision in temperature measurement. The two pairs of wires allow for complete compensation of the lead wire resistance. However, these two additional wires increase complexity and brings extra cost. So the four wire configuration is preferred for higher precision applications where our accuracy is paramount and the cost is secondary consideration. Basically, the choice of configuration depends on the specific accuracy requirement of the application and the available budget for wiring and instrumentation. Next, coming to the advantages of RTDs. RTDs have many advantages. So, because RTDs in our power plant, we can see only thermocouple or RTD, and rest other temperature measuring devices only a few. So RTDs, I would say, are the second most favorable temperature measuring devices after thermocouples. RTDs have many advantages. Our first advantage is RTDs have high accuracy and precision, and the relationship between the resistance and the temperature is linear, allowing for a precise and reliable reading. Second is RTD offer excellent stability and repeatability over time. This ensures consistent and reliable temperature measurement, making them suitable for applications where precision is critical. Our third benefit is RTDs have linear response. The resistance of an RTD changes linearly with temperature, simplifying the calibration process and making it easier to interpret temperature readings accurately. Simplicity, basically, temperature and resistance change both are one to hand to hand, basically linear response. So very simpler calibration. Next advantage is their wide temperature range. RTDs can cover a broad temperature range, making them suitable for applications that require temperature measurement in both low and high temperature environment. Next is RTDs are known for their long-term reliability and durability. They can withstand harsh environment conditions and continue to provide accurate readings over an extended period. Coming to next advantages is their standardization. You throughout this presentation, I have means lots of time use the word Pt100. So that's the standardization. The most common RTD Pt100 The platinum with a resistance of 100 ohms at 0 degrees Celsius has become a standard in many industries. This standardization facilitates compatibility and interchangeability of RTD across different systems and applications. Next is the ease of calibration. The calibration of RTD is relatively straightforward due to their linear relationship between the resistance and temperature. This simplifies the calibration process and contributes to the accuracy of temperature measurement. Also, these RTDs exhibit low self-heating effect, minimizing interference with the temperature being measured. This is crucial in application where sensors influence on the temperature is to be kept minimal. Next advantage is their compatibility with modern measurement equipment. RTDs can be easily interfaced with modern measurement and control systems. Their electrical characteristics make them compatible with the variety of instruments and controlling device. And last but not the least, RTDs have the advantage that they have application across industries. RTDs find application in diverse industries including aerospace, automotive, chemical processing, pharmaceutical, and wherever you mention. This versatility makes them suitable for various temperature sensitive process and system. In summary, I would say the significance of RTD lies in the ability to provide accurate, stable, and repeatable temperature measurement across a wide range of application, contributing to the efficiency and reliability of industrial processes and system. Definitely, they have certain disadvantages too, but those are as compared to other temperature measuring devices, or to be more precise, if I compare it with thermocouple, means then the limitation of RTDs we will discuss. First limitation of RTDs, they have limited temperature range compared to some other temperature sensors such as thermocouple. They may not be suitable for extremely high temperature application. And second is RTDs, especially those made up of platinum, can be more expensive compared to other temperature sensors like thermocouples or thermistors. This cost factor may influence the decision in budget and sensitive applications. Definitely, but budget also comes in first in a power plant when while choosing this type of instrument. Means we have to see both accuracy and budget. Then next is RTDs generally have a slower response time compared to thermocouples and thermistors. This characteristic may be a limitation in application that require rapid temperature change to be detected. Next is RTDs, especially wire wound or thin film RTDs, can be sensitive to vibration or mechanical shock. Mechanical stress can affect the accuracy of the resistance measurement and lead to inaccuracy in temperature readings. And we know RTDs can be bulkier than some other temperature sensors, which may limit their use in applications where space is a critical consideration. Again, RTDs are having rigid shape. Basically, the rigid nature of these RTD elements may limit their flexibility in certain applications. In situations where the sensor need to conform to a specific shape or contour, other types of temperature sensors might be more suitable. Next disadvantage is RTD can be susceptible to electromagnetic interference, which may affect the accuracy of the temperature measurement. Thus, proper shielding and installation practices are required to mitigate this issue. Also, while platinum RTDs are known for their linear response, other type of RTDs such as nickel or copper may exhibit non-linear characteristics, especially over a wide temperature range. Next limitation could be limited availability in exotic materials. While platinum is the most common material for RTD, other exotic materials might be needed for specific application, and the availability of RTDs in these materials could be limited, and the cost may increase significantly. Other issue with the RTDs is the lead wires connecting to the RTDs. This connecting these RTDs to the measurement circuit can affect the overall accuracy. Compensation techniques or the use of four-wire configuration are employed to mitigate these issues. Friends, despite of these limitations, RTDs remain a popular choice in many applications, especially where precision and stability are critical. So friends, that was all about RTDs used in a power plant industry for temperature measurement. Hope I am able to clear the concept well. Your valuable feedback is most welcomed. So please share your feedback in the comment section. We will meet again in our next video. Till then, stay safe, stay healthy, take care.